you can listen in with one ear if you like, or tune me out if you feel like you know what you're doing. So I'm going to graph the derivative of this, which is that double prime. So the way I would do it is first look for anywhere you have a relative max or relative min. We're going to have a horizontal tangent line, and that means the derivative there is going to be 0. So I would say at that place we're going to have the derivative be 0. Likewise, right there is going to be an x-intercept in the derivative graph, and right there, and right there. So, what's that?
You missed one.
Did I miss one? Oh, I did. Thank you. Right here. Okay. Now, then what I would do, now if you think about it, I'm going to look for where does the derivative graph have a relative minimum or a relative maximum. If you think about the slopes of the tangent lines, we're going to start over here, and it's going to be really close to 0, but just a little bit negative. And then as we move along here, it's going to go steeper negative, steeper negative, steeper. When we hit this point right there, which is the inflection point of the graph of this function, that's going to be the steepest negative slope. Now it's going to continue to have a negative slope as I go on, but it's going to start to flatten out. So the biggest negative number that we're going to get for the derivative, at least in this region, is going to be at that inflection point. So a place where our original graph has an inflection point, its derivative will have a relative min or a relative max. Okay? And likewise, here's going to be our x-intercept. Now we start going positive. A little bit positive, bigger, 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 bigger. Somewhere in here is going to be the steepest positive slope. That means the derivative graph will have its largest positive number. That is going to be a relative maximum. 0, here is going to be a relative minimum. Somewhere in here we're going to have a relative maximum. Somewhere in here where it changes from concave down to concave up, we're going to have another relative minimum. Somewhere in here where it changes from concave up to concave down, we'll have another relative maximum. And somewhere in here where it changes from concave down to concave up is going to be another relative minimum. Now I'm going to go back to the left, and I'm going to work my way from left to right because I have some targets. So like we said, it's going to be really close to 0, but just a little negative. So I'm going to start, with something a little bit negative. This is going to be a relative minimum, and then I'm going to go to where we have this x-intercept. Then I'm going to target the next relative maximum, so I'm going to say somewhere up in there. So up in here, we're going to have our relative maximum. Somewhere in this x value, I'm going to get a relative minimum. Okay, back to the x-intercept. Somewhere in here, probably not very high, I'm going to get a relative maximum. Somewhere in here, I'm going to get another relative minimum. Somewhere in here, I get a relative maximum. Somewhere in here, I'm going to get a relative minimum. Now, as we work our way to the end, this is going to be negative. It's going to flatten out and approach 0, but always be just a little negative. So it's going to approach the x-axis from below, staying a little bit negative. So there's the orange graph of f double prime. Okay, now you got to totally change gears now to go to the purple graph. So now we're looking at the yellow graph is the derivative of our function, what we're going to try to graph. So I would start by looking for where will we have relative mins, relative maxes, and shelf points. How do we find those using the derivative? Well, for a relative maximum, the derivative will change from positive to negative. For a relative minimum, it'll change from negative to positive. So you can see here, the derivative goes from negative to positive. So that is going to be a relative minimum at that x value. With me? Here it goes from positive to negative. That's going to be a relative maximum. Now this is kind of interesting because the derivative is 0 here, but it was negative to the left and it's negative again to the right. So it's going to be decreasing, it's going to be 0 for a moment, then it's going to continue decreasing. So that is going to be known as a shelf point. So we're going to put a shelf point in there. Okay. Here goes negative to positive. That's going to be another relative minimum. Okay. Now we're going to go back through, and where our derivative graph has a relative maximum or relative minimum, the original function is going to have an inflection point. So what we're saying is that as we come down here, the graph is, since the derivative is negative, it's going to be, our function is going to be decreasing, and it's going to be getting steeper and steeper and steeper and steeper until here's where that tangent line is the steepest. Then it's going to continue decreasing, but it's going to flatten out. So where we see a relative min or max in the derivative is going to correspond to an inflection point in the original function graph. So another inflection point here in the original graph of the function, and there's going to be another one here. So this place that's a shelf point is also going to be an inflection point. So it's going to decrease, and then it's going to also, and then it's going to be 0 for a moment, and then decrease some more. But it's also going to go from concave up to concave down at that place. Think like a y equals x cubed or a negative x cubed graph. So this is going to be another inflection point, and we're going to get another inflection point here. Now there's no y scaling at all on this. So you are free to start this graph anywhere you like. Way down there, next to the ground, or you could start it up on the ceiling, anywhere. So we don't know anything about the actual y values here. So we know that it's going to be, because the derivative is negative, it's going to be decreasing, and because its derivative is going to be negative, it's going to be concave down. So it's decreasing and concave down. Follow that? Oops. I think we got erasers, huh? So we are going to be decreasing and concave down till we get to this inflection point. Now it's going to change concavity, so it's going to switch to concave up. It's still negative, so we continue to decrease until we make our way to that relative minimum, which I'm trying to align with this x value here, where our derivative switched from negative to positive. Now it's going to increase until we get to this x value right here. And now it's going to change concavity. So I'm going to go to concave down until I make it up to the y-axis, right real close to the y-axis, where that's going to have a relative maximum. Now it's going to be decreasing a little bit till I get to here, where we're going to change concavity. So it's going to switch to concave up till we get, now here's our shelf point. So it's going to, it was decreasing, it was 0 just for a moment. Now it's going back to decreasing and changing concavity back to concave down until we get here. So there's our shelf point. Okay, it's a pause where it goes decreasing, 0 for a moment, decreasing, and it's going to change from concave up to concave down. Now here we're changing concavity again, right here, until we get to this relative minimum right here. Now it's going to be increasing again until I get to this x value, and it's going to change concavity and continue to increase because our derivative is positive until we get to, I think that's it. So now it's just going to, our derivative is always going to be positive, but it's getting closer and closer to zero. So this is going to approach some horizontal asymptote. We don't really know what it is, but it's going to level off there as we get to the edge of that graph. Crazy, crazy, crazy. These are tough. Okay. Then we had a 3-minute question from the homeworks or anything else.
Did you do 13 on the final review B?
Final review B number 13. The linearization?
Yeah.
So linearization is just another word for a tangent line. So when I ask you to find the linearization, it's asking for the tangent line. And we want, our function is going to be the square root of x plus 3, and we're going to approximate the square root of 398. So we want to find a tangent line at a nice value of x that is close to this one. So a nice square root close to 398 would be the square root of 400. The square root of 400 is 120. So to make this be 400, we need the x to be 397. So we're going to pick 397 as our x value. So that makes our point have x value 397. The y value is the square root of 397 plus 3 to square root of 400 is 20. Our derivative, which we're going to use to get the slope, is going to be 1/2 times x plus 3 to the negative 1/2 times the derivative of x plus 3, but that's just 1. So that's going to be 1 over 2 square root of x plus 3. So the slope is going to be f prime also at 397, which is going to be 1 over 2 square root of 400. And that's 20. 20 times 2 is 40, so our slope is going to be 140. So our tangent line is going to be y minus 20 is 140 times x minus 397. Now, to evaluate square root of 398, we need to choose for x what? Just 395. So we're going to use this tangent line, but we're going to use x is going to be 395 because that will be our approximation for the square root of 395 plus 3. So then when we plug in the 395 here, that'll give us a -2. And that'll become a -1/20th. Add that 20 over. And that's how we're going to get to 19 squared. All right. Testing again on Friday is what we do. Semester final.
Can I take the 3.6 test this Friday?
Yeah, that's not good. And remember,